Chapter 3, Relational Database Model. Our learning objective. In this chapter, one will learn, or hopefully you will learn, the Relational Database Model offers the logical view of data, not the physical, about the relational model basic components, which is relations. And that relations are logical construct composed of row and columns, also known as tuples and attributes. That relations are implemented as tables in the relational DBMS or database management systems. How data redundancy is handled in the relational database model. First of all, logical view of data. Relational database model enable logical representation of a data and its relationships. A logical simplicity returns simple and effective database design methodology. Facilitate by the creation of data relationship based on a logical construct called relations or relation. Now, characteristics of relational database. First, a table perceived as a two-dimensional structure composed of row and columns. That is correct. These are the columns, these are rows. Each table row or these represent a single entity occurrence within the entity set. Well, that's correct. 1, 2, 3, 4. There is no 1, 1, so it is only single entity occurrence that is happening. Each table column represents an attribute and each column has a distinct name. Well, this is an attribute and each one has its own name. Now, all values in a column must conform to the same data format. That's correct. So, Judy, Jaden, Grace, Freddie, they are all named and they're all varchar. Not one of them is, for example, this is name and this is text and this is an integer and so on. Now, each column has a specific range of value known as the attribute domain. And the order of row and column is irrelevant to DBMS. No problem if the ID is in here and age from this side comes in here. No problem. However, we as a human being, we like to read it first the ID, then the name and the surname and the age and city and zip code and so on. Each table must have an attribute or combination of attribute that uniquely identify each row, which is in this case we have these attributes or these ID, name, surname, and age. Now, what are the keys? Key consists of one or more attributes that determine other attributes. For example, if I know the student ID, I will be also to know the student last name or first name or etc. I will use it to ensure that each row in a table is uniquely identifiable, so there is no duplication. Establish relationship among table and ensure integrity of the data. Using this key, we could create a relationship between other tables too. Primary key is the most important key for now, and it is the column that makes every row unique, like a student ID. No two students share the same one or the same key. Now, the determination would be a state in which knowing the value of an attribute make it possible to determine the value of another. Now, it is the basic for establishing the role of a key and based on the relationship among the attributes. Example, if you know the student ID, you will also know the student name, age, first name, last name, or any other information just by knowing the student ID. So this is the determination. And we have another word, dependency. Now we have a functional dependency, which means that knowing a value, knowing A, tells you B. For example, if I knew student ID means that I know the student name too. We have determinant and we have the dependent. Now, determinant would be the student ID, and dependent would be the student name because it depends on the student ID to be revealed its name. Full functional dependencies, entire collection of attributes in their determinant is necessary for the relationship. Type of keys. composite key. Example would be enrollment that has course ID and student ID. And it is a key that is composed of more than one attribute. Enrollment key attribute would be attribute that is a part of a key, course ID or student ID. Now, the entity integrity means that a primary key must be unique, and primary key can contain no key attribute in the primary key can contain null. So primary cannot can be must be unique and cannot have any null, no null value. Type of keys we have null. Now null absence of any data value, not zero. Zero is different from null, which could represent a known attribute. A student phone not known yet, that would be null. A known but missing attribute value. For example, data should exist but not entered. An inapplicable condition would be example middle name for someone who doesn't have doesn't have any middle name. Now, referential integrity means every reference to any entity instance by another entity instance is valid. What does it mean? If a student is 10 is used in another table, it must exist in the student table. For example, I have student table and I have course registration table. If in that course registration table we use student ID number 10, it is a must we have that student ID 10 in the student table. Now we have foreign key or FK is an attribute in one table referred to primary key of another table. Can be null, can be repeated. No problem with the foreign key. Now we talked about all of these keys. This is just a revision table. And the super key is an attribute or combination of attributes that uniquely identify each row in a table. Candidate key is a minimal or irreducible superkey, a superkey that does not contain a subset of attributes that is itself a superkey. The primary key is a candidate key selected to uniquely identify all other attribute value in a given row, cannot contain null uh, entries. Foreign key, an attribute or combination of attribute in one table whose value must either match the primary key in another table or be null. Secondary key is an attribute combination of attribute used strictly for data retrieval purpose. Now we have table product, we have table vendor. The primary key in the table product is prod code. This is the primary key, and vendor code is the primary key. However, this table will need the vendors. And of course, it is not a very good practice to merge these two tables together. So I would say that we will take the vendor code and we will put it in the product code via foreign key. Then this way we created the relationship between table product and the vendor table or table of vendors. Now we have integrity rule for entity integrity. And it says all primary key entries are unique and we cannot have a primary key null. And the purpose each row will have a unique identity and a foreign key value can properly reference primary key values. So the first part would be, so we will make sure that each row has a unique identity, and then if we use it by the foreign key, there will be no problem. An example would be no invoice can have a duplicate number, no, it can be null. So in this case, for example, we have these vendors, contacts, and names and description, area code, vendor phone, and so on. The primary key should not be duplicated and cannot be null. We have another integrity rule, which is referential integrity. In the referential requirement, the foreign key must match the value in the parent. So if I have a value in here, it must match the values in here. Now, department is the parent, has department number, department name, and location. Of course, it's a primary key, and also employee number is in the primary key. However, we need this department number in another table, and that table is employee table. We will take it here. Uh, for the foreign key, match a value in the parent table or be null. Either it is 101, 101, 102, 102, 103, 103, 104, 104. Or maybe it is null, no problem with the null, as long as it is foreign key. But for the primary key, no, null is not allowed. It's possible for an attribute to not have corresponding value, but impossible to have an invalid entry. So it's okay if it was null, but it is not okay if, for example, this one was 105. Now, an illustration of integrity rules. Customer has the primary code of cus code and the foreign key agent code. Now we have an agent, only the 5 selected fields are shown, no problem with that. The agent code would be the primary key of this table, and the foreign key, we have no foreign key. We need this agent code in the customer table. So we will take this and we will put it here. If you take a look, 501, 502, 503, they are all in the same range. So there's no 504, okay? At that time, there would be a problem because it would be incorrect. Uh, how about the customer code? You see that they are all unique and there is no null. So this is primary key. Ways to handle nulls. We can first flag it. What do we mean by flag? If it was null, just don't leave it as it is. You can put NA or -1 for the integers. Or make sure that in the first place you will not have null. To put the non-null constraint, name varchar 15 not null. This not null will tell the name that you are not allowed to have null values. And unique constraint, restriction placed on a column to ensure that no duplicate value exists for that column. For example, for the email, we want to make sure that all the emails are unique and no one with the same email can uh, log in or sign in into our system twice. Relational algebra is the theoretical way of manipulating tables content using relational operators. Now, relational operators, now this is the relational set operators, which is select, project, union, and intersect. Now, relvar, a variable that holds a relation, heading or column name, and the body or the rows. Now, relational operators have property of closure. What does a closure mean? It means that the select from a table, the result would be a table again. Join two tables would be result again a table. So when we apply operations on a table, again, we will get as a result a table, not let's say anything else. We will have a table. Now we have a select which filter rows and return rows based on a condition. What do we mean by this? So if we say select all, it will select all for us. However, if I set select only price less than $2 from this table, it will bring me only those rows that are $2. Now select only P code is equal to 311452, it will bring me that row. So return row based on a condition. Where was the condition? Now this is the condition. Or let's say the price less than $2 would be the condition. Now how about the project? It would project will choose the columns or return the columns. Now what do we mean by this? Project returns specific column. Example, this is our original table. We say project price yield, it will bring us price. If we say project p descript, it will bring us this script and a price together. For example, if we say this script and a price, and if I say the project p code and a price, it will return the p code and the price together. Now we have something else. We have a union and we have an intersect. In the union, combine all row from tables, remove duplicate rows, and we have something we call it union compatible. Union compatible means that they say they have a same number of columns and same data types. Intersect says the what exists in both tables. Return only the row that appear in both tables. Must be union compatible again. Now we will take a look at the union. You say if we union this with this, this table with this table, what we will have this table. However, in here, box fan is duplicate. Duplicate box fan, we have it in here and also in this table, so it will remove it and then it will bring us the entire table. So combine row for form two tables. Combine rows from two tables. These rows from these two tables and make it one. And remove the duplicate. We see the box fan in here. In here, when we union it, there will be only one box fan. And the table must have first the same number of column 1 2 3 1 2 3. So yeah, these two they have the same number of column and same data type. The p code, now we have the is here in here is a number, also in here number. P descript in here is a text or a varchar, also in here the same. The price in here is 1600 and the price also in here is the same. Now intersect. It will intersect these two, and what is different, it will return that. Now let's take a look. We have Franklin Lopez, William Turner, Franklin Johnson, Susan Rogers. Now we have Martin Lopez, we have Franklin Johnson, we have Peter Robinson, we have James Smith, and we have George Jones. And you can see that we have Franklin Johnson in here, so it will return that one for us. So it will intersect these two in which row they are common, which row they have both in that exists in the employee name and the staff name also. It will bring me that. So Frankel is in here, also Franklin is here, so it will return this for me. Now, relational set of operators. Please take a moment and read this slide and then I will explain it. Now, we will talk about the difference, okay, and product, what each one means and what is the job of each one. Now, the difference, return all rows in one table that are not found in other table. So we have two table. It will return all the rows in for example, table number one that does not exist or not found in the other table. For example, student in class A but not in class B. Again, for the difference, table must be union compatible. As we said, same number of columns and same data type. Now, what is the job of product? Product return all possible pairs of row from two tables. Now, for example, I have two tables. Okay, table A has 3 rows and B has 4 rows. The result would be 12 rows for the product because it will return all the rows in the both tables. Let's say that we have 3 tables and each one has 3 rows. That would be all of the rows in the tables. Now join. If we wanted to join two tables, allow information to be combined from 2 or more tables. It is not only 2. We can have a join between 3 or 4 tables. For example, we have a student plus enrollment to get student name with the course. Now, it is not only this. You can also have student, enrollment, faculty, and for example, finance to get the name of those students that have, for example, this course and didn't pay for the course. It is only we can have this feature if we used join. if we join two or three or more tables. Now we have another thing, divide. Divide, use a one two column table as the division and one single column table as the divisor or divisor, yeah. Now, what does it mean? What does the divide mean? The concept is find a value that are related to all values in another table. For example, find the student who took all the courses. Now, this would be divide. Find one student or all those students who took all the courses. For example, in our university database, we want to find how many students took all the courses. For example, 5 courses are now open. Let's take a look on how many students enrolled for all 5. Okay. Now we have the 3 types of join: natural join, equijoin, theta join. Now, in order to understand each type of join, we will have an example first. Now, in natural join, we have the student ID name, and we have enrollment that has student ID and courses. Now, the natural join, what did natural join did? Will match the rows in student ID in the same. Now, let's take a look at the in the definition. Link tables by selecting only the rows with a common value. Now, in these two tables, student and enrollment, the common value would be student ID. Select student ID, okay, and selecting the rows of student ID. Of course, student ID by itself is nothing, so it will select the rows with a common value in their common attribute. Now, we'll match rows where student ID is the same. Equijoin, join tables using an explicit equality condition, which is this. Now, explicit equality condition, you manually specify the condition. For example, select all from student S. We will talk about why this S and why this E in the our lab session or the video that we will record it for you. Okay. However, the equijoin says select all from student and enrollment. Now, when should we select all? Only where this condition is true. The the student's student ID is equal to enrollment student ID. Now, equijoin will tell me all those students that have enrolled in a specific enrollment. Now, theta join would be more general form of join using by any comparison operator, which is these. Now, these will call theta join. Equal, greater than, smaller than, equal, and greater than, smaller, and equal, and not equal. Example, join where salary is greater than budget. For example, you would say select all from students, okay, or join students on enrollment when where salary is greater than the budget. Type of joins, we will have inner join, outer join, left outer join, right outer join. Now, inner join only return the matched record from the table that are being joined. Example, only students who are enrolled in the courses. Now, outer join returns matched and unmatched rows. Unmatched values are filled with null. Okay, because we said matched, for example, we have 10 matched rows. Well, no problem. However, what about the unmatched rows? It would be null. Still, outer join will return us this. Left outer join return all rows from the left table and matching the rows from the right table. Example, we have 2 tables. These 2 tables for the left outer join return all the rows from this left table and match rows from the right table. If no match, null on the right side. Right outer join, the vice versa of this, return all rows from right table and matching rows from the left table. If no match, again, null on the right side. Now we have differences. In here, we talked about differences. We said student in class A but not in class B. Now let's see here. George, George Jones, Jane Smith, Peter Robinson, and Franklin Johnson, Martin Lopez. Now, if we difference this one with this two, it will return these. George Jones has in here, but not in here. There's no George Jones. Now, Jane Smith, yes, there's no Jane Smith. Now we have the Peter Robinson. Again, Peter Robinson, we have it in here, but no Peter Robinson in here. And Martin Lopez, we don't have Martin Lopez in here. However, Franklin Johnson, we have it in here and we have it in here. So the difference will not return that for us. Product. In here, we said that the product, it will multiply the, if we said that we have table A and product table B, we will have all the rows in both tables. Now let's take a look at the picture. We have a flashlight, lamp, box fan, 9-volt battery, and 100-watt bulb and a power drill. If we product it with this, we will have this multiplication. Why? Because 1, 2, 3, 4, 5, 6, 6 by 3, we will have this. Now for flashlight, we have a flashlight, we have a lamp, we have 3 lamps. As you can see, for each one we have 3. Flashlight, 3, lamp, 3, box fan, 3, and 9-volt battery, 3 power drill, and a bulb. So it's a multiplication. Multiply this by this. For the flashlight, we have 526, 526, 23 watt and W and 5. We have also for the K 24, we have that for the 25. So for each one of these, they will all have the same criteria of this table. Now this table will be used in our illustration for join. Now we have divide. Divide is this A, 3A, 2B, 1C, 2D, and 1E. If we divide this by this code, we will have the location 5. It will return as this. Now let's see why divide will return this for us. Because we said find student who took all the courses. For example, use 2 column on a table that division and 1 single column table as a divisor. What was the concept? Find value that are related to all value in another table. Now A5 will be our code and it will be our return. Data dictionary and system catalog. Before explaining this part, guys, do you have any question? Anything?
No.
Okay, thank you very much. And now that there's not a lot of students, again, we will take it for like 15 more minutes and then we will stop the class. Now, a data dictionary and system catalog. Data dictionary is description for all tables in the database created by the user and the designer. This would be the data dictionary. A description for all tables. Now, what about the system catalog? System catalog is the system data dictionary that describe all objects within the database. Now, this is somehow, data dictionary is somehow more general. The system catalog is more related to the database itself. Now we have 2 terms that must be avoided to lessen confusions. Homonymous and synonymous. Homonymous means same name is used for different attribute. Make sure to avoid this. Example, name is used for staff name and supervisor's name. If you want to use name, this word name, make it this way, STF, which stands for staff. For example, you have table staff, and if you wanted to use name, don't use name directly. Say staff name. For example, ID, staff name, age, and for example, city. Now for the supervisor name, don't say name directly. Say name directly. Don't say name or in the you have a table name supervisor. Don't write it name. Say supervisor name. Now synonymous. Different names are used to describe the same attribute. This is a problem that leads to inconsistency. For example, staff name and employee name. Now staff name and employee name are the same. For example, in a table. So why two names? Only use one standard name and stay with it. However, for the tables, we don't have only divide, we don't have the project or product and so on. We have relationships because we know that a table with another table, it has some kind of relationships. They need to have some type of relationships. Now we will talk about these relationships, and the first one would be one-to-many. One-to-many relationship. This is norm for relational database or the most common relationships. What does it mean? It means that one department can have many students. For example, I have created table department and I have table students. I need to make sure that this one department can have many students or my database will allow me this when I create the tables for department and students. So from the side of department would be one, from the side of students would be many. One-to-one relationship, this one is not very common actually. We are using it only in some special cases, and it would be one entity can relate to one entity and vice versa. We have many to many. It means that many students can take many courses and of course cannot be implemented directly in relational databases. We have some tricks to do it, however, not directly. We cannot have many to many or M to N. M to N is not directly supported by a relational database. We can have it in the non-relational database, which is the MongoDB and the others. However, no, in the relational, we cannot have this type of many to many or end to end. We will have something to do. We will have some tricks to do, but not directly. Now, the composite entity or bridge entity or associative entity will solve this problem for us. It helps avoid problem inherent to M and M relationships. So it solves this one. Now convert M to N into 1 to M relationships. Example, student plus courses create enrollment table. Now that you cannot fix the problem of students and courses, what you can do is to create an enrollment table and have the ID of student and ID of the courses together in that table. That would be called composite entity. And of course help to avoid this problem that we have because in our database we will need many to many relationships, however not in this form, not in many to many. We will use composite entity and we will create one table between these two tables that need to be many to many. Now this is the figure one, and this is one to one. Professor chairs department. Now, what does it mean? A professor chair one department, and the one sign is this, these two lines, and again these two lines in the side too. A department can be chaired by one professor. Now, the bidirectional relationship begin each sentence with singular, read both ways, and the red were put in the diagram. What do we mean? We mean that the professor chairs one department, and one department can be chaired by one professor. So it is bidirectional. We can read it in the both ways. Now, this was the one-to-one relationship. How about M to N relationship, to one M2 relationship? Now, you see we have this. We have students, many students has many classes. However, we said that in relational database, this is not allowed. Now, how to solve it? We will put enroll in this between. Now, the enrollment would be in this between. Instead saying that the students has many students, this is the sign for many, or the M. Instead of saying student, many students has many classes, we say that one student, the student, now you see the relationship changed. Okay, we gave this many to this enroll, the both sides, and the other side would be one to one. Now we will explain it. Now, what does this diagram means? It means that one student, why we know this is one, because this sign, this is the sign for number one, and we said one student registers in many enroll, and one class shows in many enroll. Now the enrolls will contain the ID for ST and for the class ID. CID. Now in here we say SID. Now the enrollment will have these IDs. For example, says SID number one is equal to, or the has course ID of number two. Now again, the student ID number one can have course number three. Student ID number one can have course number four. For example, this is security, this is programming, and this is database. However, how to solve it in here? In relational, we cannot. But in if we use composite entity, we can use it this way. We will put, for example, in this case, we had student, we had class. We will bring another table as this enroll, and we will have the ID of each table in this table. This is how we will fix the M2N or many-to-many relationships. Now, guys, do you have any question about this? I mean, M2N or composite entity in general?
No, thanks.
You're welcome. Now, let me erase. Now, changing M2N relationship to 1 to M relationships as we explained it in here. Now, here's the text. I explained it in here, correct? However, we have also this. And now, a student has many classes. A class can have many students. The bidirectional relationship begin each sentence with singular and read both ways. The red word put in the diagram. We can read it this way or this way. You can say student has many student has many classes, or can say many classes has many students. Now let's say that this model that we have it in here, we will expand it. Now we have the expansion as this. We say that one student can register in many enroll, and many enroll shows in classes, in one classes, because this is one, this is many, this is many, this is one. Now we can say many classes has one course. For example, this is information technology, of course. Now we have the many classes for information technology. And we have many students that they all can enroll for those classes. This is the expanded ER model or entity relationship model. ER stands for entity relationship model. Now, composite entity, more example. We have customer, we have orders, we have order line, we have product. Now, between the product and the orders, we have the order line. Now, we want to make sure that many product will have many orders. However, this is not available for us. Now, we did it this way. We put the order line or this table, we brought this as a mediator between them. And we say that one product can have many order line and one order can have many order line. Now, if you can see that we have a primary key product number and we have order number. Now we have order number and product number. I said the previous example for in here that the student ID and the class ID would be in here. Now as you can see, product number is in here and the order number again is in here. So this will create the relationship between this and that. Now also this is the expanded one. We will have the orders and we will have customers. Now, many customers can have many orders. Again, it would be the same thing. If we wanted to, we need to fix it and bring another table in here, and we call it uh, for example, the customer orders. Not only orders, customer orders. Now, the relational diagram for the invoicing system. This is, again, another example to make sure that you understand better. You see in here we have number one, and in here we have this infinity. This infinity means many, one to many, one to many, and many to one. Now, one customer can have many invoices. By another word, I go to a supermarket. It's only me, but I can many invoices. I can say that give me, for example, rice and oil in one invoice and give me the beverages in one invoice, and they will give me no problem. So one customer can have many invoices. And one invoice can have many lines. Now, the line will contain invoice number, line number, product code, and line unit and line price. And many lines can have one product. So one product can have many line and one customer can have many invoices. And of course, the relationship between invoices and lines would be one to many. Now, before going any further, guys, do you have any question? Anything
No,
that is
thanks.
ambiguous, nothing, something that you don't understand? Okay. Now we have something we call it data redundancy. It means that we have duplicate data. In the first slides, we said that the duplicate data is a problem because it leads to inconsistency. Same with the same name, one name for two things that are the same. How a data redundancy again will have inconsistency and it is a problem. DR or data redundancy. If I said DR, I mean data redundancy. Now, DR means storing the same data multiple times in a database. Well, now someone might ask me, well, if I have a database, why should I have the same data multiple times in a database? Actually, I'm saying that this is a problem and you should never allow this. However, it sometimes happens and sometimes for good reasons. Now, relational database facilitate control of data redundancy through use of foreign keys. Now, if I wanted to have data in three tables, A relational database says, well, please do not duplicate these data. Instead, I will give you foreign key, and if you wanted that data, just call it using the foreign key, and I will show you. However, must be controlled, except the following circumstances. Well, we say that the data redundancy should not be allowed by anyone. However, we have, of course, special some circumstances. And the first one would be if for performance reason, to make queries faster. However, if your database is like 2 gigabyte, don't make it 4 gigabyte. By another word, if don't let half of uh, your data be redundant. Another one would be for historical data to keep past records unchanged. We have something in database which we call it log. Now, this logs for a system, for example, tells you that, for example, system administrator changes the permission. System administrator changes permission again. Administrator changes the permission of, for example, user number one. Now, in this time, we will need it because this is a history. We want to make sure that even if the data, if the system administrator of some system, let's say the student system, changes one student's course registration, we want to make sure that we will know who did that and how many times did it change. He changed it from what to what. That's how, in that case, we will also need the data redundancy, except the performance reasons and historical data. And believe me, the historical data is the one that you should be considered. For the performance reason, always there's a reason that you can do to not have data redundancy. However, for the historical data, we can do nothing for it. Now we have a faculty data. Now, faculty in USA means academic or staff lecturers, just so you know. Now, a fac supervisor is FK, referencing fac SSN can have a null value and can be redundant. No problem. We said that a foreign key, no problem, can be redundant, can be null, as you can see in here. Fac supervisor is FK. Faculty supervisor is FK. We can have redundancy. For example, in here, 1098, 1098, no problem. This is foreign key, no problem. Let it be redundant, let it be duplicate. And also we can have null, still no problem, as long as it is foreign key. But faculty SSN is the problem because this one is the primary key. We should not have duplicates in here. And if we have it, it is a problem. Because if we have a duplicate in here means that, for example, this one, Leonard Vince, and the fact rank is assessed and the faculty salary, or let's say lecture salary is this much, it would be duplicated. This, and we will have it in here. In the previous slide, data redundancy, we said that we should not have the multiple data at one time. So we should make sure that data redundancy problem will be solved as much as we could. Because sometimes, as we said, for the historical purpose and for making queries faster, in a quotation, of course, making query faster, because sometimes, for example, rookies will not know how to design a good database. They will have many redundancy. And they say, well, if actually, this is why I did that, because if I call it from that table, it will take some time. So if I call it from here, my database would be faster. No, it is not like that. If you use the foreign keys in an efficient way, you will not have that problem, believe it or not. Now, the hierarchical data display, we displayed it in here. However, we will also display it in here. So you see Victoria Emmanuel has Leonardo Fibin, and Leonardo Fibin has these two, Leonardo Vince and Christopher Colon. Now, where's Victoria Emmanuel? Victoria Emmanuel. She's a professor. Okay. Now, let's see Leonardo Fibin. Leonard Fibin. Leonard Fibin. Well, you may ask me, what does it mean it has, or in here, why this is the relationship? Because you see that the serial number for Victoria became foreign key for this. Okay, so it means that Victoria Emanuel is the supervisor for Leonard Fibin. And we know this, she's professor and this person is associated professor. So it makes sense. Now, sorry, how about the Leonardo Fibin has these two, Leonardo Vins and Christopher Colon. Leonard Vins, Christopher Colon. Now you see that the Christopher Colon and the Leonard Vins, they both have this 1098, 1098. And the 1098 is the serial number for Leonardo Fibin. So it means that Victoria Emanuel supervised Leonard Fibin, and Leonard Fibin supervised Leonard Vins and Christopher Colon. This is just a display. It is better to understand this way instead of this, because you need to have a very good eye to see these. Now, let's say that Victoria Emanuel, we have 0987. Let's see, 0987. Supervise this. Now, how about this itself? 1098. Supervise how many? Well, 1098, 1098 means that we have these two. So to supervise these two persons. Now, how about the Julia Mells? Has a professor or has a supervisor? Well, yes. And the supervisor is Nikki Macon, because the in the foreign key this has been said. Now you see they don't have anything. These are nulls. No problem. Okay, there's no problem if it is null. There is no problem if we have duplicates. Okay, no problem at all. However, it is a problem if we put this one in a range that there's no that serial number. That is a problem. Now we have this definition for the here fac SSN, first name, last name, and the fac rank, which would be staff or lecturer rank. It means their title, assistant, or of course, assistant here is assist professor and a professor and associated professor. We have faculty serial number, faculty first name, last name, faculty city, state, zip code, faculty hire, faculty department, and faculty supervisor. We set some constraints or some rules, strict rules, to make sure that this will happen. Now, PK, faculty, primary key, and faculty SSN. Now, PK faculty means and primary key FSSN. Now, FSSN means that the primary key is the SSN. We will make sure to make the fac SSN as a primary key. This is ruled, so no duplicate will be in here. And no null, we will have no null also. Now, also we say that the faculty supervisor would be a foreign key. And the referencing, or we will take it from the table faculty. Now, also, this is faculty supervisor. It is foreign key, and they took it, although the table is not in here, they took it from the faculty table. As it says, references faculty. Now, again, another example of one-to-many relationships. Guys, I will explain only this slides and then we will stop. The one-to-many, one student can have many enrollments, and for example, one course can have many offering, and one offering can have many enrollment, and so on. So what you need to understand is read this. Student one. It means one student. Now, how about this enrollment many? Okay, one student can have many enrollment, and this is how we would rate it. Let's see. We will stop at this slide. Now, one-to-many relationships. Rows of each table are related to multiple rows of other table. Not directly represented in a relational model, as we explained, use two one-to-m relationship and associative table. Give an example of one-to-one, one-to-many, and many-to-many. We explained these in the previous slides. Now we have reference rows. Reference rows is a foreign key referencing row in associated primary key table. Enrollment rows refer to a student and offering. Example, a student has a student ID and it is a primary key. However, in student ID in enrollment would be a foreign key. The student row is the reference row. As action on reference row, what happens when you delete a parent row or update a primary key? Okay, these are the questions that you should know by now. Now, reference row actions. When a row in a parent table changes, we must decide what happens to related rows in the child table. This is for sure. Important rule, referential integrity must not be violated. And we explained it in the slide number 9 or 10 was it referential integrity. Example, if a student is deleted, what happens to the enrollment? So you should not allow deletion of a student because we have it in the enrollments. Possible action that you could do. Restrict, do not permit action on a reference row. Do not permit student row to be deleted if there's any related enrollment rows. You have two tables, for example, three tables, students, enrollment, and courses. You should restrict the delete of the student row because it will affect the enrollment and the courses too. Cascade, perform action on related row. Example, delete related enrollment row when student row is deleted. For example, instead of making sure that you would restrict because now you want to delete a student row, you should do also delete in the enrollment table too. Now, possible action again, the third one would be nullify. Set the foreign key of related row as null. That's another option. Or set the default. You see in database sometimes we have default value. You can set the value of that uh, section as a default one. Now we have a SQL syntax for action. Now create table enrollment, offer number integer not null. Make sure that it would not be null. STD SSN character not null again. And enrollment grid decimal 32. Now we have some constraints. Constraint number one would be PK enrollment, and the would be the primary key offer number and STD SSN. Now constraint number two, FK offer number or foreign key offer number is a foreign key from the offer number table. References in offering, which is the table, and this table will have an ID. That offer number would be the ID for the offering table. On delete or restrict, on update cascade. It means that when someone wants to delete, restrict it, do not let them to delete. And on update cascade. In cascade mean perform action related to delete related enrollment when student row is deleted. Now constraint FK, STD, and SSN would be a foreign key, which is the STD student S serial number, and it came from the student table. Again, on delete restrict, on update cascade. Now, these are the support materials that you can also watch in YouTube video or in this website or understanding this chapter, integrity rules and constraints, especially. And these are the review question, the final exam, April 2010, question 2. This was the one of the questions. And the relational database below contain detail about Kirti Malay Behat, KTMB train, journey from Kuala Lumpur Central to various destinations in Malaysia. Now, A, create all the relationship using SQL commands specifying the integrity constraint and the action on a reference row. Now, once we have these line, it means that they are primary key. And thank you very much.